Hello everyone, welcome back to Decking Cards. So today we'll be taking a look at an interesting coding problem, and I've chosen this problem because it doesn't require advanced data structure or algorithm knowledge. It can actually be tackled by logical thinking and reasoning things through. So if you have been following Math Olympiad problems on this channel, be assured that this will still be a very good problem for you to watch. So without further ado, let us take a look at this problem statement. Okay, so the problem is taken from a recent Codeforces round and it's titled Red Light, Green Light. So the problem statement is as follows. Now as usual, the problem statement can be quite long, so I've broken it up across a few slides. Okay, you are given a strip of length 10 to the power 15 and a constant k. There are exactly n cells that contain a traffic light. Each traffic light has a position pi and an initial delay di, for which di less than k. Okay, the I traffic light works the following way. It shows red at the lk plus di second, where l is an integer, otherwise it shows green. What does all this mean? So basically you have your very long strip here. K is basically like the period. The traffic light behaves in a way where it is a cycle of period k, and basically di is the offset during which the traffic light will show red. So for example, over here in this diagram, I have two traffic lights. So my strip is horizontally displayed, and I have two traffic lights, one at this position and the other one at this position. And let's say k equals 2 is the period. So if di equals 0 means the offset is 0, then the traffic light will show red at all multiples of 2. Correct? Because of this formula here. Whereas if di equals 1 means the offset is 1, then it will show red at all multiples of 2 plus 1. So that's why the red is at the odd timings. Okay, so far, hopefully this is quite easy to understand. Now, you are initially positioned at some cell on the strip, let's say here, facing the positive direction, so facing rightwards in our diagram. At each second, you perform the following actions in order. Firstly, you check if the current cell you're on contains a red traffic light. If so, you turn around. Now, regardless whether there's a red traffic light or not, you also move one cell in the direction you are now facing. So, for example, you start here at time equals 0, you check is there a red traffic light? No, so you don't need to turn around, but then you move one cell forward, so that's why you end up here at time t equals 1. And then, same thing, you move forward, and you are here at time t equals 2. And over here, there is a red traffic light at where you're standing. So you turn around, but you also still move in the direction you're facing one cell. So you end up here at t equals 3. That's why you're here at t equals 3. And in this scenario, you notice that, you will actually end up bouncing back and forth. So one thing you realize is that you cannot actually escape in this scenario, because if you bounce at this traffic light from the left and go back facing left, and you end up bouncing at the same traffic light again in the same direction, means from the left going back to left, then you can easily reason with yourself that because the traffic light patterns loop every k period, every period of length k, having this bouncing basically means that this pattern will just repeat itself over and over again. It's the exact time of this bounce doesn't matter. The fact that you bounce at a certain chunk in a certain point in the period tells you that this behavior is going to repeat. This exact behavior here is going to repeat itself again when you hit this traffic light again from this direction. So then you just keep doing this over and over again, and you never escape. So what is the actual problem you need to do? You are going to be given q different starting points. for each one, determine whether you will eventually leave the strip within 10 to the 100 seconds. Now 10 to 100 is just chosen to be very big, so that basically you just need to determine whether you will loop or you will actually not loop, which means you will eventually escape. So in this scenario, we have already explained why you will be looping. And here's another example. You start here instead. You can very quickly check that actually you end up escaping. And same for this example over here. And just one comment that escaping from the left is also counted as leaving the strip. So you can escape either from the left or the right of the strip. Okay, so hopefully you have a good understanding of the problem now, and it is actually quite easy to remember and intuitive to remember. But one more thing is the size of the constant. So this is very important for programming problems. So in our problem here, the length of the strip is 10 to the 15. Number of traffic lights will be up to 2 times 10 to the 5. And the period is up to 10 to the 15. The position of traffic lights is going to be given in increasing order, and it can be anywhere on the strip, so it's up to 10 to the 15. Delays of traffic light is basically the remainder mod k, so the offset will be from 0 to less than k. Then the number of queries, another very important one, it can be up to 2 times 10 to the 5 queries, so that's quite a lot of queries. And the starting positions can be anywhere on the strip. So what do this size of the constants mean? Well, basically in a programming problem, the general rule of thumb is you should be aiming to do only up to 10 to the power of 8 computations or reasoning steps, because you are only going to be given like 1 or 2 seconds for the code to run, and rule of thumb is 1 second equals 10 to the 8 operations. So this means you cannot look to do something like algorithm that needs n times q number of operations. It needs to be linear in n, linear in the number of traffic lights, or linear in the number of queries, or n log n, q log n, things like that. So if you're not familiar with the asymptotic behavior, just treat it as you want to find something that is efficient, and let's see how to do that in this problem. Okay, so let us first approach this problem not caring about the time constraint, and let's first consider solving this for one query. And if we want to do this, it's quite straightforward. You just simulate the process. You pretend you start somewhere at the given starting point. You roll forward in time until you figure out what's the first traffic light you meet, if any. If you never meet any, it means you actually escape. But if you hit some traffic light, then the question is, after bouncing from that traffic light, what is the next traffic light that is met, if any? So again, you simulate walking backwards now. See whether you meet any red traffic light. If not, you escape. If so, you repeat step 2 again. So you keep repeating step 2. Eventually, you will either escape or you will realize that you have hit the same traffic light from the same direction as something you have done before, which means that you actually are now in a loop. Okay, so sounds like a reasonable way to find out the answer, but it's incredibly inefficient. So, for example, you just roll forward in time, you might take up to 10 to the power 15 before you even hit one bounce. Now, even if you instantly figure out what traffic light you hit at, you can hit up to n traffic lights before you get the answer, and you need to do this for every query. Then n times q is going to exceed the time limit. So we need to do better than this. But nonetheless, let's first figure out how to do step 2, which is the crux of this whole thing. You need to figure out, after bouncing from a red light, what is the next red light that you will meet, if any. So how do we do this? Let's say we just bounce off this red light from the right. So going back to the right and going forward. And this traffic light is at position pi with offset di. Now we know that the time now is then some time that has value congruent to di mod k. The question is, what is the next red light that is met? So one thing you can do is look at the next traffic light and see if by the time I make it to this traffic light, is it going to be red or is it going to be green? So let's check this. Let's say the next traffic light is at pj, dj, at pj with offset dj. Then the time to make to that next traffic light is pj minus pi. So if the time now, which is t plus the time taken to reach there, is congruent to dj mod k, then it will be red. If not, it will be green. So you can do this check, and then if let's say it's green, then you check for the next traffic light instead, and you keep checking until you check all the traffic lights to the right, which is still a bit inefficient, but bear with me. This is a good start, and we can actually even make this check even simpler to handle. So right now this check seems a bit tedious, but you can actually do a trick here. So t is congruent to di. I'm going to plug this in, and if I rearrange the terms, I actually get this condition instead. So I just need to check the p minus d value. If the p minus d is congruent to the p minus d of the first traffic light, the original traffic light that you bounce at, then it will be red. If not, it is not red. So very easy. I calculate the p minus d here. Then I take the remainder mod k. I check p minus d here. Is it same? Remainder? No. Then I check, is this same remainder? No. Then I check, is this same remainder? And so on. So, okay, it sounds a bit faster now, but I still have to check so many traffic lights. But this gives you a very good idea, which is I can just group the traffic lights by their p minus d values. So I'm going to define a dictionary called rightword class, where the keys are the p minus d value, and then the values are basically a list of all the traffic lights with that p minus d value. Now, a word of warning, when you create this dictionary, do not by default insert all key values that are possible, because the key values can go up to 10 to the power 15, and then you will just run out of time again. So start off with a blank dictionary, and then only insert a key when you discover a traffic light has that p minus d value. So we can actually put all the traffic lights into their respective p minus d class in linear time by just going through the traffic lights one by one. So far we haven't violated the time limit because I'm only taking order n steps. And what you can do is, for example, first traffic light, p minus d is 14. Then I'm going to just create key 14 and insert that traffic light index into the list. Then over here, okay, p minus d equals 3, create the key insert. Now, that is all good, but actually what we want is to know what is the next traffic light quickly. So what we can do again is pre-compute this answer or lookup table by defining a dictionary called rightword next. So if I'm heading to the right and I just bounce off light I, what is the light J that will be the next red traffic light that I meet, if any? And again, this can be computed in order n. In fact, you can do this while creating the rightword class, because whenever you insert a new traffic light, let's say this one, into its class, you just need to check, is there existing traffic light in the class? If so, look at the last one that has been inserted. Then this means that from this traffic light, if you bounce here, you'll end up meeting a red traffic light here. So again, all this can be done in linear time, and the key point here is you can pre-compute this lookup table before you even get any query, and you do this only once. No matter how many queries you will have, this lookup table is going to be very useful later on. Okay, how about bouncing from the left? So bouncing from the left, you can do a similar analysis. The time taken to the next traffic light will instead now be pi minus pj, because pi is larger than pj. So if you do the same analysis and rearrange the terms, etc., you'll get the condition now is to look at the p plus d values. So I'm going to create same thing leftward class where the keys are p plus d values. and slot in the traffic lights that have that P plus D value. And I'm also going to create the leftward next lookup table where if I bounce at traffic light I from the left, what is the next traffic light that is going to be red? So same thing, you can pre-compute this in order n. Okay, now that we have this very useful lookup table, we know that when we bounce at traffic light, what is the next traffic light that will be red, and we can look this up in one operation. The thing is we are interested in escaping, not just the next traffic light. So we can repeat looking at what is the next traffic light, the next red traffic light, the next red traffic light, and so on until we get outcome. So this suggests that maybe we should now try and build up a lookup table for partial answers. And by partial answer, I mean answers to the following question. Suppose I just bounce at light I from the right. Do I eventually escape? Yes or no? I want to have this answer ready on hand so that I can look up in the future. So let's think about how might we compute this given our previous lookup table. So let's start off with a set called scene. This will document all the bounce conditions you have seen before. And by the problem itself, I'm going to start off with light I bouncing from the right. So this will be the first entry in the added to the set. From here, I use my previous lookup table. I know what is the next traffic light I'll bounce at from the left. And then I'm going to add this to scene and then check for the next traffic light that I bounce at and so on and so forth. Now, eventually, two scenarios happen. If you end up at a bounce that you have seen before inside this set, then you know that you have actually entered a loop and the answer is that you have failed to escape. The other scenario is you bounce off a traffic light and then you check, oh, you are actually not going to meet another red traffic light. So it means that you actually eventually escape. So you have found the answer to this particular question, but the key insight is that the same answer will apply to everything that you have seen so far in this set over here. Because if you were to start the scenario again from one of the bounces inside here, you are going to do the rest of the simulation in the exact same way again and reach the same answer. So you can actually, from this one simulation, get multiple answers, not just answer for this bounce scenario, which means that you could possibly build up partial answers of all forms in a very efficient way. So that's what we're going to do now. We are going to pre-compute a dictionary called partial answers and do this in, again, on time. This dictionary basically has a bounce scenario here at light I bounce left or light I bounce from the right. And the value is a boolean that answers this question. I just bounce at light I from that direction. Do I eventually escape? And basically, to populate this dictionary is very straightforward. You look through each possible scenario. So look through for each pair light I direction. If you already know the answer, you can then skip. If you don't know the answer yet, then you simulate the process. You start bouncing. And you check where's the next bounce using the first lookup table. You keep bouncing until you hit a pair, which means a bounce scenario where you know the answer, maybe from a previous computation, or you end up in a loop, or you end up escaping. And once you have this answer, you then update the answer for all the pairs in scene during the series of bounces. So basically, if you have already seen the answer before, you won't end up visiting the bounce again extensively. So that is why this dictionary can be computed in linear time. Yeah, even though for some starting scenarios, you have to bounce a few times before you get the answer. But then those that you already bounce, end up you don't have to check for them later on when you reach them because you have already recorded the answers for them. So pretty straightforward. And now we still haven't answered the question for an arbitrary query, but we have all these pre-computed tables which we have done in linear time, and they are going to be incredibly useful for answering an arbitrary query. So to answer arbitrary query, you start at A, which is the given starting position. You still need to first find out what is the first traffic light it bounced at, because A need not be a traffic light. So you can't use your lookup table yet. But it's also very easy to find the first traffic light it bounced at using the same trick. So firstly, by doing the exact same analysis that we've done before, you'll realize that the first traffic light or the traffic lights that will be red for the person will be traffic lights that have P minus D congruent to A. So this means that what we can do is look at our right word class. Remember we had this earlier. Then slot A into that particular P minus D class. So look at that P minus D class. I mean, if it's empty, it means you will never meet a red traffic light. But if there are traffic lights inside this class, you need to find the first traffic light that is on or to the right of that. So these are all the traffic lights with the same P minus D. So if the A is at this position, then the first traffic light to the on or to the right of it will be the first traffic light that it bounces off. So to find what is this traffic light, you can do binary search. You don't have to check one by one because there's a risk of you taking n. But if you do binary search, then you can actually find that traffic light in log n time. And after you found the first traffic light, you are bouncing off that traffic light from the left. You can then use your lookup table to determine if you bounce off that traffic light from the left, will you escape or not escape? And from there, you get the answer in order 1 time. So each query can be overall answered in order log n because of the binary search, which makes the total time complexity q log n, and therefore it is within our time limit. So very interesting problem. I hope you enjoyed that problem. Well, for future videos, we are going to do some math-oriented problems because the IMO is coming. And I hope you will subscribe to the channel and stay tuned for those videos. See you soon.